Hello, my name is Roy Simpson. I'm a professor of mathematics at Cosumnes River College in Sacramento, California. This lecture is all about reviewing multiplying and factoring polynomials, and we'll discuss actually in part A what a polynomial is. We'll talk about the parts of a polynomial, things like binomials, monomials, trinomials, degrees of polynomials and monomials, that type of thing. And then in part B, we'll focus on multiplying polynomials, which is should be a review. All of this should actually be a review for students in an intermediate algebra or college algebra course. However, I'm supplementing any type of in-class review with this review video. Finally, part C will be factoring polynomials. It'll be more of a factoring strategy and just a recall of the factoring methods, and then we'll go into some factoring problems. The first object we're going to talk about here is a monomial. A monomial is just an algebraic expression, not equation, but expression, having only one term, such that all variables have natural number exponents. A few quick examples are monomials like 3xy squared. Notice it's only one term, there's not a plus something else or a minus something else. Notice that each of the variables have a natural number exponent. The y has an exponent of 2. The x has an exponent of 1. We just don't write it in there. It's a habit not to. Another example of a monomial is negative 13 halves, r to the 15th, x, z to the 28th. And you notice, by the way, here, it is a single term. There's no addition or subtraction going on between these factors. And then even though the coefficient here is a fraction, that's totally fine. The only other requirement is actually that our variables have powers or exponents that are natural numbers, which these are. Remember, natural numbers are 1, 2, 3, 4, 5, 6, those numbers. And let's go ahead and just write one more. Pi times x, y. I'm just too lazy to do anything else. Pi xy is also an algebraic expression because pi is just a number. So it's just some number times x to the first, y to the first. And there's no other terms here. It's only a single term. Something that I wasn't going to define, but I thought as I was talking about this that it'd be a good idea. These numbers that hang out in front of the variables, these are called the coefficients. So I'll define that. There we go. The coefficient is the numerical factor of a term, and it's usually written in front of the term. So the numerical factor of this first term is the 3. And remember, a factor is just when you factor a number, you factor into products. So this term here, this first example, has 3 factors: a 3, an x, and a y squared. And actually, you can have more factors. You could say it's a 3, an x, and a y, even. You can get even more detailed than that. But when we're talking coefficients, we usually just wrap up the entire number here and say that's the numerical factor. So like negative 13 halves is the numerical factor for the second monomial. And that, therefore, negative 13 halves would be our coefficient. So let's go ahead and go on to our next definition. This next definition really talks about how we can identify how powerful a monomial is. The fact is that some monomials are more powerful than others. And so this kind of helps us out. We have something called the degree of monomial. It's the sum of all powers, which are the exponents, on the variable factors. So, for example, let me go ahead and switch to my example pen. If you consider that 3xy squared, the degree here, well, we have x to the first, y to the second. So 1 plus 2 would be 3. Basically, this means that as far as how powerful it is, it's, if you think about it, a power level 3, if you think video games. Whereas the next monomial, which is a negative 13 halves, r to the 15th, x, z to the 28th, the degree on this one is much higher, which means it's a much more powerful monomial. We have r to the 15th, x to the first, so that's 16 altogether, plus another 28 for the power of z. So that should be, I think, about 44. That's a pretty powerful monomial. What do I mean by power? It means that if I were to let r, x, and z be 2 in this monomial here, the value, the resultant value, after I said what's r or what's 2 to the 15th times 2 times 2 to the 28th, that would be much larger than if I were to let x and y in this first monomial be 2. 2 times 2 squared would be just 8. That's nothing. But 2 to the 15th times 2 times 2 to the 28th, that's huge. I mean, huge. So that's what we mean by degree, is that when you substitute in the same numerical values for the variables in both monomials, you'll end up with the more powerful or the higher degree monomial, you'll end up with a much larger number. Finally, I want to throw a wrench into the works here. Let's try something like 2 to the 18th x squared y z. There, we'll do that. Well, in this case right here, it's not very much of a wrench in the works if you just follow the definition. Definition says that the degree of a monomial is the sum of the powers on its variables. So the variable x has a power of 2, the variable y has a power of 1, variable z has a power of 1. 2 plus 1 plus 1 is 4. You do not take into consideration the power on the constant, because constants do not contribute to the degree of a monomial. So you can ignore any of the constant powers. Or I should say powers on the constants. So let's do a little exercise. Which of the following is a monomial? And more than one could be. So, or that's the idea, is that we could identify possibly that more than one could be a monomial. We'll find out if any of them are actually. That first one, 3 times x to the negative first y z, that is actually not a monomial. It's not. And the reason why is because, remember, monomials have to have powers that are natural numbers on the variables. The issue is the x to the negative first. That's an issue. That power -1 is not a natural number, so we cannot call this a monomial. The second one, let's verify that we have one term here. We do. Let's verify that the powers on the variables are all positive exponents, or actually I should say natural number exponents. That's x to the second, which is a natural number, and y to the first, the 1, is a natural number. So it does seem to fit. This is a monomial. The third one, part C here, x plus y squared z, that actually has two terms in it. We have a term here and a term there. So this is not a monomial. Remember, mono means one. So this has two terms. So we have a special name for that. And finally, this last example, which is an important example actually, I didn't really mention it down when we originally defined it. We defined a monomial as an algebraic expression having only one term such that all variables have natural number exponents. There's a subtle thing that must be mentioned. It's that the variables cannot occur in denominators. The reason why is because if they do, and you know a little bit about negative number exponents, then this could be written as 3x to the negative 1, which means that this is also not a monomial. So a very important thing to remember is that you cannot have variables in denominators to be a monomial, and you'll find that that is true also you can't have a variable in a denominator to be a binomial, trinomial, or a polynomial. Speaking of binomials and trinomials, let's go ahead and define those. A binomial is just an algebraic expression involving two monomial terms, and a trinomial is an algebraic expression involving three monomial terms. Bi means 2, tri means 3, and Let's go ahead and just write a couple examples down of each. An example of a binomial is something like 3x squared z minus pi times rst. Notice each of these terms, and there are two terms here. There's the second term here, and here's the first term. Terms are always separated by addition or subtraction. The first term is a monomial because all the powers on the exponents are natural numbers. And the second term is also a monomial, again, because of all the powers on the exponents are natural numbers. And you can do these examples all day. Just as a reminder, this business RT over Z plus 1 over X is not a binomial because neither of those are actually I have to write this down. I can't talk and write sometimes. Because neither of these are actually monomials. So this is not a binomial at all. And a trinomial is just as easy to kind of show. Trinomial, you have this business where it's, let's say, 1.2 xy minus 3.8 z, we'll call it xn, x squared, minus 1.112 z. That is a trinomial. You have three terms, 1, 2, and 3, all separated by addition or subtraction. And each of those terms is a monomial. There you go. Now, of course, you could have I'm sorry, I shouldn't say that word yet, but I will. You could have algebraic expressions involving more than three terms. But once you get to more than three, we just give it one general name. We call them polynomials. A polynomial is just an algebraic expression involving two or more monomial terms. Now, it's interesting that if we have two monomial terms, we normally would call that a binomial, but by this definition, it could also be called a polynomial. Poly just means many, and to some people, two is many. If you have, if you're being robbed and you have two robbers, that's too many, right? That type of thing. Okay, so a binomial is called a polynomial. A trinomial is called a polynomial. Some people actually like to call monomials polynomials, even though that's actually not true. There's once you have if you have only one object, you don't have many of them. You only have one. So I usually just call them all polynomials, but in reality, monomials should be monomials. Everything else can be a polynomial. Okay, so there is a double definition. So, like I said, this first example here is a binomial and a polynomial. That's a trinomial and a polynomial. And then here's an example of something that's neither a binomial nor is it a trinomial, but it is a polynomial. Let's say x plus 2y squared minus 3xz plus 4xyz. There we go. And so in this case, we have four terms. You could even have 20 terms if you want, but that's a polynomial. And finally, what we should talk about is the degree of a polynomial, because just like monomials themselves have a degree to them, a certain level of power, polynomials do as well. When I say polynomials, you should know that I'm speaking polynomials, binomials, and trinomials. They're all polynomials. The degree of a polynomial is just the degree of the highest degree monomial term in that polynomial. That's a little bit of a mouthful, so let's take an example here. And then I'll describe it to you how I generally teach it in a classroom. So let's find the degree of the following polynomial. Let's do 3x to the fifth minus x plus 1. Technically, that's a trinomial. We can call that a trinomial, but it's also a polynomial. What we would do here is we'd go through this and try to find the highest degree monomial term. So let's look at each of these terms. And I'll start with the rightmost, not that you would have to, but I'm starting with the rightmost just to kind of show you something about that rightmost term. that rightmost term is just a constant. There's actually no variables. And remember, the definition of the degree of a monomial is the sum of the exponents on its variables. There's actually no exponent here. So as a reminder, so recall, oops, that's not how you spell recall. Recall that the number 1 can actually be written as 1 times some other number that's equivalent to 1. And x to the 0th is equivalent to 1. X to the 0th is 1. Y to the 0th is 1. Z to the 0th is 1. So really, you can think of this as a 0-degree monomial. So just a little note, I'll write as a note, constant terms are 0-degree monomials. That's something that is you can just carry with you from this point forward. You know that if you have a sentence, an algebraic expression here that has a constant term in it, then you know that term has a degree of 0. In other words, it has very little effect on this overall polynomial. The degree on this second term here is just 1, and the degree on the first term, or the first monomial, is 5. Let me write the degrees above it so you can kind of see what I'm talking about. This is degree 5, 1, and 0. So obviously, of these degrees, the highest powered or highest degree monomial term would be this first term. So that would be the degree of the polynomial. This implies degree of polynomial is 5. Notice the difference between finding the degree of a polynomial and finding the degree of a monomial. A monomial, you would add up the powers on the variables. But for a polynomial, you look through all those monomials first and find their degrees by adding up the powers on those monomials. And then, once you write down all those numbers, you take the largest of those numbers. You don't add up 5 plus 1 plus 0 here. It's just the most powerful one of that group. Let's do another example, and then I'll explain why this is true. So another example would be something like the same instructions, find the degree of, okay? Let's do this. Negative x plus 3xy minus pi times x squared y cubed plus 0.000001 x to the 6th. And if you look through each of those terms, basically each of those monomial terms, let me highlight each of them here. So that first term, you would start asking yourself, well, what's the degree of that monomial? That's degree 1. That second term is a monomial, and degree of that is x to the first, y to the first, so the degree of that monomial is 2. The third term, which is also a monomial, it has to be, has two variables, x and a y, and their powers are 2 and 3. Add those up, you get a 5. So that's a degree 5 monomial there. And finally, the last term is actually the easiest to find the power on. The degree of that monomial is a 6. Right, x to the 6th. So it turns out the degree of this polynomial is 6. It's the highest of those powers. Now, let's go and talk about why we call 6 the degree of the polynomial, whereas with monomials we normally add up the powers. It turns out, and this is how I usually describe it in class, if we manipulate this last example to rewrite it in what we call descending power order. So if I were to write, I don't know how many zeros I put there, I think 5. If I were to write this in descending power order, I'd have 0.000001 x to the 6th minus pi times x squared y cubed plus 3xy, and then finally minus x. If we were to write it in descending power order, I generally call the largest degree monomial term the bully on the block. The reason why I call it the bully on the block is because over the long haul, that that lead term, that highest degree monomial term, ends up being the most powerful term in this monomial. In other words, when x is 1 and y is 1, let's pretend, when x is 1 and y is 1, it really makes no difference. They're all, I mean, that's going to be 1 to the 6th and 1 to the 2nd and 1, whatever. But when x is a billion, some huge number, well, if you're considering a billion to the 6th power, that's insanely huge. You actually cannot fathom that number. A billion squared, well, that's a big number, but it's nothing compared to that billion to the 6th power. And then a billion times, maybe, let's say y was 2. A billion times 2, hardly anything. And then minus a billion, chump change. Let me demonstrate this in a simple example. Let's say that a person's salary is determined by the following polynomial. So we have this x squared plus 500x plus 21,000, where x is just the number of days. Now, this is not a real polynomial description of somebody's salary, but this is just an interesting example that might reinforce the idea of when or why the degree of this polynomial would be considered to be 2. Why we don't care about the last two terms. Well, okay, day 1, you would let x equal 1, so you get 1 squared plus 500 times 1 plus 21,000. Now, this is a great job, by the way, because day 1 you get $21,000 plus an extra $500, so that's 21,500 plus an extra dollar, so it's 21,501. Now, that extra dollar is chump change, right? You don't really care about that. But let's see what happens. Maybe, I don't know. Let's say a year down the road. A year down the road, you have 365 squared plus 500 times 365 plus 21,000. Now this one I'm likely to need a calculator for, so I'll go ahead and bring up my handy dandy graphing calculator and clear out all this stuff. Now 365 excuse me, 365 squared plus 500 times 365 and then plus 21,000. And we get some huge amount of money. What is that? $336,725. That's awesome. But now I got to ask, really, it seemed as though that 21,000 initially, this 21,000 here, the lowest powered monomial in this entire sentence, that initially was such an exciting number. We thought 21,000, wow, that's awesome, because then, the very first day, that's the bulk of our money, that 21,000. But now look, as time has gone on, that 21,000, well, that makes it gives us 21,000 extra dollars, that's fine. But out of the money that we're making, we made $336,725. That 21,000 is chump change. That we really didn't need that extra $21,000. So already a year later, who cares about that monomial term? Now let's see about maybe 10 years later. So let's pretend we're 10 years down the road. So that's 3650, so 3,650 days down the road. So here we go, 3650 squared, that's how many, basically x is number of days, so I'll just plug that in for x. So I get 3650 squared plus 500 times 3650. And again, that additional 21,000, but at this point, we don't really even care about that additional 21,000 because it's going to be so small. Now let me show you each of these numbers in turn and what they are. 500 times, so I'm just calculating that middle term here. That's a lot of money, right? $1.8 million. That's a pretty significant chunk of change there. So that's not something to scoff at. However, let's see what this first term is. 3650 times 3650. And you immediately see that's 13 million. $13,322,500. And all of a sudden, really that 21,000 means very little now. It's absolutely it's junk. That fell out of our pocket on the way to work. That type of thing, right? And slowly but surely this middle term starts to become less significant as well. It turns out if you did this for 20 years, um, the first term, which is dominated by the x squared, the first term would give us all the money basically that we would ever possibly want. And then the second term would be, we could just throw that out at the end of the day. We could care less about that second term. This is why, a very trivial example, but a good example to kind of illustrate why the lead or the highest degreed monomial term in a polynomial is called the degree of the polynomial. It's because that's the term that ends up over the long haul as x gets large being the bully on the block, being the one that dominates the values that this polynomial takes. I mean, those other little things are chump change. They'll have a little bit of an effect, but not a large one. So we are often interested in what is the highest degree monomial term, because that'll tell us some huge piece of information over the long haul. That's why we're so interested in the degree of a polynomial.